Hello, and welcome to the finale of section 5.4. So at the end of last video, I actually lied a little bit. There are no more theorems in this section. All I want to do is look at sort of a slight generalization of what we did last section. And then I want to do one example and do a couple theory questions. So, remember last time we showed that if A was diagonalizable, right, that is, A was similar to a diagonal matrix D, and we looked at that basis B formed by the eigenvectors of A, then D was the B matrix for the linear transformation T sub A, representing matrix multiplication by A. And so it turns out we can actually generalize this idea to any matrix C, even if C isn't diagonal, that is similar to A. This is because this matrix P has to have linearly independent columns. And so we can let a basis B be defined as the columns of P. And then it turns out that if I let, again, this linear transformation above B defined by multiplication by A, then the B matrix for T is actually this matrix C, which is similar to A. So this is actually just basically stating the same thing that we did last video, except that this actually, it turns out, holds for any matrix that is similar to A. So that is any two matrices that have the same eigenvalues. Any two matrices that are similar. I made the mistake that I warned everyone not to make. Any two matrices that are similar actually represent the same linear transformation, just represented under a different basis. And it turns out we can relate these two bases using this matrix P, which performs this similarity transformation. So I want to do one example in light of looking at this fact, and then we'll do some theory questions. So now we're going to look at the matrix A equals 4, 4, negative 9, negative 8. And then we're going to let B be a basis for R2, where B1 is equal to the vector 3, 2, and B2 is equal to the vector 2, 1. So what we want to do is let T sub A of x equal A times x be a linear transformation from R2 to R2. And we want to find the B matrix for T sub A. All right, so we actually have to call on the last fact in a little bit of a different way than maybe we were expecting to. So notice here, B1 and B2 form a linearly independent set, right? And so again, if we think about what's going on, we've got this vector x going down to its B representation. And so we want to find this matrix, right? we want to find this matrix here that is mapping the B representation of X to the B representation of A times X. But so remember what we learned is that if A and C are similar, two matrices are similar, under a specific linear transformation, or under a specific matrix P that defines a basis, then it turns out that these two matrices, right, can go here. So, you know, if I can find a matrix similar to A using the right similarity transformation, then I can find the B matrix for T sub A. Specifically, I'm going to let C equal the following matrix, P inverse AP, where P is the matrix whose columns are equal to B1 and B2, right? Because then this transformation is defined by the columns of this matrix performing the similarity transformation. And what we already know then is that this matrix C, which is similar to A under this matrix P, is going to be the B matrix for T. So using determinants and our inverse knowledge, I calculated that P inverse was equal to -1, 2, 2, -3. And so that means that C is equal to a long string of matrix multiplication and if you go through all of this multiplication, you get the following matrix. And so interesting notes about this matrix. This matrix isn't quite diagonal, right? But because it's upper triangular, this means we actually know the two eigenvalues of A. And I think, let's see, so -2, -2, yeah. These actually then turn out to be the two eigenvectors of A. So B1 and B2, as it turns out, are the eigenvectors of A. This is actually called the Jordan form of A. It's a very, very interesting, like I said, eigenvalue theory just tends to be really interesting. It's this very interesting type of matrix which we can sort of show is always similar to A and encodes some really nice information about the matrix. So if you're enjoying eigenvalues, definitely look up Jordan canonical forms because they're a very interesting sort of progression of eigenvalue theory. So anyways, if we're given this basis, given this matrix, we just have to let C be the matrix defined by this similarity transformation, and it turns out that this matrix C is also the B matrix for T of A. All right, so like I said, I want to wrap up with a few theory problems that are included in this section to just get a little more work on those. I think all of these will be under the guise of always true. So sort of just want to go over, like, when we've decided that something is always true, how do we go about proving it? So we want to show that all of these statements that are always true. And so the first statement says that if A and B are n by n matrices, and A and B are similar, then A squared and B squared are similar. So again, I highly encourage you to try to prove all of these on your own. It'll go a lot like some of the shorter proofs we've done, where you start out with some sort of equation that you know, and then you kind of rework it into the equation that you want. So with these, always, write an equation that you know, write an equation that you want, and try to figure out how you can turn what you know into what you want. So what do we know? Well, we know that A is equal to P times B times P inverse for some invertible matrix P, but we don't really care what P is. So this is what we know. What do we want? want to show that a squared is equal to q times b squared times q inverse. Or maybe q is an invertible matrix, but we don't exactly know what q should be. And usually in this case, maybe a good guess is the matrix that we already know. Well, so if we want a squared on the side by itself, maybe a good thing to do would be to just square the equation that we already know. Well, look at this. If we work out this matrix multiplication, notice that this p inverse and p cancel each other out. We're left with two b's in the middle, which form a b squared. And then we've got a p and p inverse. And again, this is enough to show that the two matrices are similar. So not only are they similar, right? But they're similar to the they're similar using the same matrix to show this similarity transformation, which is very nice. So there's sort of 4 questions, 1, 2, 3, and then a bonus challenge question. I'm going to do 2 and then leave 3 and the bonus question for you, but I'll post the solutions at a later date. So the second question says that if A is similar to B and B is similar to C, then we want to show that A is similar to C. So again, we want to find some sort of similarity relation between A and B, or A and C, excuse me. And what do we know? Well, we know that A and B are similar, right? So we know that we can write A like that. We also know that B and C are similar, so we can write B like that. Right? So these are the 2 things we know. And again, what we want to find is some sort of relationship between A and C that is a similarity relationship. So in this case, what you want to do is you want to start out with an equation for A or an equation for C. In this case, we have an equation for A, but we don't want B in this equation. So maybe a good idea would be to substitute an equation in terms of C for B. So these 2 equations imply that A is equal to P times Q times C times Q inverse times P inverse. But notice I can sort of reshape these parentheses here using my matrix multiplication properties. And so this is equal to the matrix PQ times C. But notice that this matrix here is actually equal to PQ inverse, right? PQ inverse is equal to Q inverse times P inverse. And so this is A matrix times C times an invertible matrix equal to A, meaning that A and C are similar. So, like I said, there's one more theory question on there for you to practice. It'll involve a proof very similar to how these 2 went. So I recommend trying it. It's quite short too, so it should take a couple lines of sort of working with equations to show that it's true. And then if you want the bonus challenge question, if you want maybe something that's a little more challenging but kind of in the same light as these 2, I encourage you to look at that. But anyways, that wraps up section 5.4. So next we'll move on to 5.5.